Quick fact about Jupiter's moons. The giant planet has nearly 100 of them. Most are tiny captured rocks and debris that barely register. But 4 are massive, large enough to be worlds in their own right. We call them the Galilean moons, named after Galileo Galilei, who spotted them in the early 1600s using one of the first telescopes ever made. Callisto, ice and rock, heavily cratered, geologically dead for billions of years. Ganymede, the largest moon in the solar system, also mostly quiet. Europa, a frozen shell hiding a liquid water ocean beneath, one of the best places to search for life. And then there's Io. Io has up to 400 active volcanoes, lava lakes the size of small countries, mountains that seem to have burst straight out of the ground, a surface painted in vibrant sulfur compounds. It's the most volcanically active body in our entire solar system, more active than Earth, more active than anywhere else we've ever found. So what's driving all this chaos on a moon that, by all logic, should be frozen solid? In this video, we'll break it down in a way that's simple but scientifically accurate. Here's what makes Io confusing at first glance. Io orbits Jupiter at a distance of about 217,000 miles. That's roughly the same distance between Earth and our moon. But there's a critical difference. Io is in the outer solar system, far from the sun. At Jupiter's distance, solar energy is so weak that most moons are frozen solid, dead, geologically quiet for billions of years. Outside of volcanic zones, Io's surface temperature drops to approximately minus 202 degrees Fahrenheit. That's colder than anywhere on Earth. And yet, right next to those frozen plains, you have active lava flows and erupting volcanoes. Fire and ice side by side. So where does all this heat come from? It's not the sun. The sun is too far distant to provide meaningful warmth. The answer is gravity, specifically the gravity of Jupiter and the other Galilean moons working together in a way that turns Io into a heat engine. Before we explain what's happening on Io, it helps to understand a process called tidal heating. You already know about tides on Earth. The moon's gravity pulls on our oceans, creating high tide and low tide as the Earth rotates. In the open ocean, that rise is only about 1.6 feet on average. Different coastal areas experience more dramatic changes based on geography, but in deep water, the effect is relatively subtle. But here's the key insight that most people miss. Gravity doesn't just move water. Strong enough gravity can deform solid rock. And when rock gets stretched and compressed over and over again, it generates heat, the same way bending a metal wire back and forth makes it warm to the touch. The mechanical energy of flexing gets converted into thermal energy. That's tidal heating, gravitational forces causing physical deformation, which generates internal heat. On most moons, this effect is minimal, but Io is a special case. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. Io is caught in a very specific gravitational trap that exists nowhere else in our solar system. On one side, Jupiter, the most massive planet in the solar system, with gravity powerful enough to physically distort Io's shape. At Io's close distance, Jupiter's pull is immense. On the other side, the 3 other Galilean moons, Europa, Ganymede, and Callisto. They're not nearly as powerful as Jupiter, but they exert their own gravitational influence on Io, pulling it in the opposite direction. Here's what that creates. The competing gravitational forces prevent Io from settling into a nice circular orbit. Instead, Io follows an elliptical path, sometimes closer to Jupiter, sometimes farther away. It never gets consistent gravitational exposure. Io completes one orbit every 2 days. Every 2 days, it cycles through the strongest and weakest points of gravitational pull over and over, forever. The result? Io is constantly being stretched when it's close to Jupiter, then released when it moves away, then stretched again, then released again. This has been happening for billions of years, and all that mechanical flexing generates tremendous heat. Here's where the numbers become impressive. When Io reaches its closest approach to Jupiter, the surface bulges outward by as much as 330 feet. That's not water moving around. That's solid rock being physically lifted and then dropped back down. For comparison, Earth's ocean tides rise about half a meter. Io's rock tides are 200 times larger. All of that mechanical energy, the energy of an entire moon being squeezed and released every 2 days, has to go somewhere. It goes into heat. Enough heat to melt rock, enough heat to power hundreds of volcanoes simultaneously. Io is essentially a giant stress ball being continuously squeezed by Jupiter's gravity, and unlike a stress ball, it can't stop. The gravitational forces never turn off. If you picture a volcano, you probably imagine a steep mountain with lava and ash erupting from the top. That's how most volcanoes work on Earth. Io doesn't work that way. On Earth, volcanoes typically form along plate boundaries, areas where tectonic plates collide and force molten rock upward. That's what builds the classic cone-shaped mountains. Io doesn't have plate tectonics. There are no continental plates crashing into each other. Its volcanism operates on completely different principles. 1. Lava erupts from fissures, cracks that form when the constant gravitational stretching fractures the surface. 2. The eruptions are violent. The initial release can throw molten rock dozens of kilometers into the sky. 3. Above the lava, plumes of sulfur gas can rise for hundreds of kilometers, visible from orbit as enormous umbrella-shaped clouds. 4. Instead of building mountains, the eruptions tend to collapse the surface. Molten rock fills the resulting depressions and creates giant lava lakes. The largest lava lake is called Loki Patera. It measures approximately 124 miles in diameter. In the center sits a large island of solidified rock surrounded by an actively churning lake of molten material that scientists have been monitoring for decades. Every photograph of Io shows wild colors: yellow, red, green, white, blue. It looks almost artificial, like someone painted it. It's completely natural. All those colors come from sulfur chemistry. Sulfur is consistently present in Io's volcanic activity. When eruptions happen, sulfur gas rises into the atmosphere. Eventually, it settles back down and coats the surface in layers of sulfur compounds at different temperatures. Here's what creates each color. Yellow equals crystallized sulfur, essentially sulfur snow that has settled in the cold regions between volcanic zones. White and blue equals frozen sulfur dioxide, found in the coldest shadow areas where temperatures are most extreme. Green equals sulfur monoxide, created when Jupiter's intense radiation belts interact with sulfur in the upper atmosphere. It's a chemical reaction powered by radiation. Red equals active hotspots, areas of recent volcanic activity where sulfur is still being heated and hasn't cooled down yet. The entire moon is coated in these compounds. Different temperatures, different chemical states, different colors. That's what makes Io look painted. Here's where Io gets even stranger. If Io's volcanoes collapse the surface rather than building it up, where do the mountains come from? We got our best answer from NASA's Juno spacecraft. Juno arrived at Jupiter in 2016 on a 5-year mission to study the gas giant's atmosphere. After completing that primary goal, the probe was repurposed to investigate the 4 Galilean moons. In December 2023 and February 2024, Juno completed 2 close flybys of Io, passing within 930 miles of the surface. What it photographed was one of the most unique landscapes in our solar system. Scattered across Io are tall, isolated mountain peaks, not mountain ranges like on Earth, just lone spires stabbing straight up into the sky, seemingly at random. One of the most striking is called Steeple Mountain, rising between 3 and 4.3 miles high. Its shape resembles a church steeple, or the Eye of Sauron, if you prefer that comparison. The tallest mountain on Io reaches approximately 11 miles. That's roughly double the height of Mount Everest, and it stands completely alone. The current theory is surprisingly elegant. When a major eruption causes part of the surface to collapse and form a depression, all that downward pressure has to go somewhere. It doesn't just disappear, it pushes on the surrounding rock. In many cases, that pressure forces a nearby section of rock to pop upward, like squeezing one end of a tube of toothpaste and watching something come out the other end. So sinkholes and mountains appear together. For every depression that forms, a peak may rise somewhere nearby. But that's why Io's mountains are isolated spires rather than continuous ranges. They're not built up gradually by geological processes. They're pushed up suddenly by compression. This is a type of mountain building that exists nowhere else we know of, and it's been happening on Io for billions of years. The surface in a constant state of rise and fall, shaped by the relentless pull of Jupiter's gravity. Here's the unfortunate reality. The Juno images might be the last detailed views of Io we receive for quite some time. Juno is slowly running out of fuel, and its mission will eventually end. The two major upcoming missions to the Jupiter system are both focused elsewhere. JUICE, Jupiter Icy Moons Explorer, launched by the European Space Agency in 2023. When it arrives in 2031, it will investigate Ganymede, Callisto, and Europa, studying their icy surfaces and the liquid water oceans believed to exist beneath. Europa Clipper, launched by NASA in 2024, arriving in 2030. As the name suggests, this mission is dedicated specifically to Europa and the search for conditions that might support life. Neither mission includes Io as a primary target. Why? Two reasons. First, timing. We didn't fully realize how fascinating Io was until those Juno flybys happened just a couple of years ago. Mission planning operates on decade-long timescales. By the time we understood what we were missing, the next generation of probes was already designed and built. Second, priorities. Io almost certainly doesn't harbor life. No liquid water, surface too harsh, constant volcanic destruction. Meanwhile, Europa and Enceladus might have subsurface oceans with actual biology. When you're deciding where to spend billions of dollars, the moon that might have aliens tends to win. But priorities change. Leadership changes. New technologies emerge. At some point, somebody will want to take a closer look at the most volcanically active world in the solar system. Io is a reminder that the universe doesn't always do what we expect. A moon that should be frozen solid is actually on fire. A surface that should be building mountains is collapsing instead, and creating mountains anyway through a process that exists nowhere else. Somewhere in those volcano-scarred landscapes and impossible peaks, there are still secrets we haven't figured out. Questions about planetary formation, about energy transfer, about what's possible in extreme environments. The images exist, the data has been collected, and eventually we'll send something back there to learn more. Until then, we'll always have Steeple Mountain. Io is just one of the extraordinary moons hiding in our solar system. Europa may have a vast ocean beneath its ice. Titan has lakes of liquid methane. Enceladus shoots water into space. Watch our video on the most dangerous moons to discover what else is out there.